So we're going to look at vector equations of lines rather than Cartesian equation of lines. Now I'm going to do it in 2 dimensions first, and then we can push that idea through to 3 dimensions. All right, here's a line. I've got 3 points on the line, and their position vectors would be A, R and B. Now what I do know then is that the vector AR is some multiple of the vector AB. So if I work that out, I can say, well, R minus A is equal to lambda B minus A. Let's say R is the unknown, so R is equal to A plus lambda B minus A. And that now gives us an equation of the line, but in vector form. So that's the format of a vector equation. Now, let's go and show that actually it does turn out to be the same as y equals mx plus b. If I give some coordinates to A and B, written in column form, so R is the unknown, so xy, one of the points there, x1 on y1, and then lambda would be x2 minus x1 on y2 minus y1. Break that into the 2 components. They would be the parametric equations of the line. If I make lambda the subject, that's the key with the equation of the line. That actually now is the Cartesian equation of the line. It's just not in the format that we're used to seeing it, because we don't normally say is equal to some constant value. But that is indeed the Cartesian equation of the line. To prove it, let's just play with these first two terms. If I was to cross multiply, but of course y2 minus y1 and x2 minus x1 is the slope, and there is the equation of a line. It's our point slope formula. So it does turn out to be the same thing. So if they're now asking me to find the equation of this line, but a vector equation rather than a Cartesian equation, there's my answer. Write it down straight away. Of course, I could have written it down that way. But what have I done? Well, basically, I've said that it's any point on the line, but it's the position vector of that point. Now, I had 2 points. I could have written 3 minus 5, but equally -2, -8, because they're both points on the line. Plus, some multiple, basically the direction vector of that line. How do I find the direction vector between 2 points? Well, head minus tail. So 5, 3. Now it doesn't matter. I could have also had it as -5, -3. Because I'm multiplying by lambda, and lambda could be positive, could be negative. I suppose it makes more sense to have those numbers being positive. They don't have to be. The actual Cartesian equation would have been this: y equals 3/5 x minus 34 and 3. Now have a look at the direction vector and have a look at the slope. They're very similar, but it's upside down. Because of course when we're writing our vector, our column vector, the x is on top, not the y on top. Whereas in slope, we have the y on top, rise over run. Now look at this then. Remember in complex numbers, rotation of 90 degrees was multiplication by I? Let's sort of play with that idea. If I had some vector and its slope would be rise over run, but I've written it in column form, so it's run over rise, and I'm multiplying that by I, you can think of it that way, multiply it out, and I end up with minus rise over run. So in fact, A over B is perpendicular to minus B over A. So that's sort of proving that the rotation of is. How? Well, because if I use the dot product and got AB and minus B on A, sure enough that turns out to be 0. Okay, so yes indeed they are perpendicular. If I now had to find the vector equation of this line, you can pretty much write it down straight away. Because what have I got? I can pick any point on the line, any one I like, and write down the position vector of that point. I chose -2, 1. And then the other one is the slope. Remember the slope, when I'm writing as a column vector, we call it a direction vector rather than slope, and it looks like the reciprocal of the actual slope, and the slope of this line would be -2/5. So I've just turned it upside down. And so that's the difference. Notice it says find a vector equation. It doesn't say find the vector equation, because there's an infinite number of vector equations you could write down. It could be any point on that line you could write in there. But I had to find the point of intersection of these 2 lines then. The first one, as a vector equation, I could write this way. 0, -1 plus lambda, 1, -2. The vector equation of the other one, 3, 0 plus mu, 5, -3. If I equate the components, so on the top one, for the x component, I would just have lambda. On the bottom one, I've got 3 plus 5 mu. And with the y components, Top one, I've got minus 1 minus 2 lambda, bottom one minus 3 mu. Okay, let's go and solve that. Mu equals -1. I now know mu is -1, sub it in, and I've got the point. I just got to do a bit of calculation now. And there it is, -2, 3. We're going to find a vector equation that joins these 2 points. That will allow us to write some parametric equations for any point on the line. And then we're going to find where it intersects the parabola y equals x squared. Well, there's a vector equation. I picked the first point, -1, 1. Could have just as easily picked 4, 11. Lambda times the direction vector, head minus tail. Now you might be looking at this and thinking, hang on, 11 minus 1, that's not 2, and 4 minus -1, that's not 1. Basically, I've simplified it down, because remember, it's times lambda. So lambda could be anything. X is -1 plus lambda, y is 1 plus 2 lambda. They're the parametrics. I want to find when it intersects y equals x squared. So let's sub that into y equals x squared and find out what lambda is. And we get 2 possibilities, lambda equals 0, lambda equals 4. And that kind of makes sense when you think about it. If I've got a parabola and a line, it should be cutting it in 2 places. Oh, unless it's a tangent, I guess. Sub those lambdas in and we get our 2 points. Okay, in 2022 they asked this one. Okay, they've given us a vector equation rather than the equation of a line. And it's telling we've got this other line which passes through this point and is parallel to this first line. So all it's essentially saying is find the equation of this line which is parallel to another line and goes through a point. Well, the direction vector is 3, 2, which means the slope is 2/3. It's parallel, so it's got to have the same slope. I've got a point that it goes through, point slope formula. There's the answer. Let's push the idea into 3 dimensions then. If I want to find the equation of a line goes through 2 points, it's not going to change because we're dealing with vectors. It's still going to be A, which is the position vector of some point on the line, plus lambda times the direction vector, the direction that vector is going into. So now, if I want to find the equation of this line, again, I can now just write it down. Any point on the line, I chose the first one, 1, 2, 3, plus lambda times the direction vector, head minus tail, 3, -5, -1. We have our equation. What is the Cartesian equation? We now can't write a simple y equals mx plus b down, because we've got 3 variables here. And that's why I go back to that idea of, hang on, we make everything equal to lambda. And that's what we're going to do here. Actually, we're going to make lambda the subject of each of the components. And there's the Cartesian equation. It's unusual. You're not used to seeing 2 equal signs in an equation of a line. But that's because we've got 3 components. And we're saying all of these 3 components would be equal. Last year, this one. See, now, this is more like an extension 2. It's in 3 dimensions now. Find the vector equation of the line. So it starts off, okay, find the vector equation. I need to work out the direction vector, so 4, -5, 6, but there it is. Pick either of the points. I chose 3, 5, -4. Part B, determine whether this point lies on the line. Well, the idea doesn't change from 2 dimensions. How do we show a point lies on the line? We substitute it in and see if it works. But there's another way I could do it. If I found the direction vector AC, and in this case it's 7, 0, 2, that direction vector, because it's lying on the line, would have to be the same or some multiple of the direction vector of the line if it lies on the line. And it doesn't, because there's no way I can manipulate 7, 0, 2 by just multiplying by a real number and get some multiple of 4, -5, 6. So as AC is not a scalar multiple of AB, that means they're in different directions, so C can't lie on L. 2020, they've given us 2 lines. We've got to find the point of intersection of the 2 lines. Well, that means their components must be the same. So if I look at the x component, I know 3 plus lambda 1 must equal 3 minus 2 lambda 2. All right, I've got a relationship there between lambda 1 and lambda 2. Lambda 1 must equal negative 2 lambda 2. Now let's look at the y component. Negative 1 plus 2 lambda 1 is negative 6 plus lambda 2. But hang on, we just said lambda 1 was negative 2 lambda 2. I've now got a value for lambda 2 equals 1. But does that mean that's the point of intersection? Because there's a third component as well. That would have to be equal as well. So let's just check, subbing into the third one, and again I come up with lambda 2 equals 1 as well. Okay, that's making me confident then. By substituting it into the third component, it confirms that those lines intersect. Now actually, the way this question is worded, I didn't need to do the third one because we've been told they do intersect. And because I only came up with one possible solution for lambda 2, then that must be the one. But if they hadn't worded it like that, yes, I would have to confirm it in the third one and go, yeah, these are going to intersect. Well, substituting that value in to either line, we can come up with, well, there's the position vector. They've asked us for the point. There's the point 1, negative 5, 5. Line passes through that point parallel to this one. Again, similar sorts of questions, but now in 3 dimensions. Well, we know that two lines will be parallel if their direction vectors are multiples, well, scalar multiples of each other. So there's the equation. Minus 2, 1, 4 is a point on that line, and it has to have the same direction vector. So it will be some multiple of 2, 1, negative 2. What about if we had to find two are perpendicular? Now we used to say, well, the slopes are the negative inverse of each other. But that was in 2 dimensions, and that's not quite the same in 3 dimensions. So it's the dot product we're going to have to use. We know the dot product is 0 when two vectors are perpendicular. Okay, so the direction vector of this one is 1, negative 1, 4. Dots, this is the direction I'm trying to find, so I just call it A, B, C. But I know that would have to equal 0. That gives me a relationship. A minus B plus 4C is equal to 0. So there is the line. I just don't know what ABC is equal to. But I know that it's going to be equal to some multiple of the 1, negative 1, 4. Equate the components. Lambda A is equal to mu and so on. Well, I'll say 2 plus lambda mu is minus lambda A. That's substituting the first one into the second one. 3 plus lambda C is 4 times lambda A, substituting the first one into the third one. I now come up with what lambda is, and I get another expression for the relationship between A, B and C. Now, combine that with the first expression, we got simultaneous equations. So B equals 23C on 7. But here's the thing, because if it's going to be some multiple of the direction vector, I can pick any number I like for C or B, doesn't matter, because I'm going to multiply it by some real number anyway, which is some. So make it easy for myself. I'm going to let C equal 7 and that just cancels. So B is 23 and therefore A is negative 5. I now have the equation of the line. So if two lines have their direction vectors, B1, B2, I know they're going to be parallel. If B1 is equal to mu B2, they'll be perpendicular if the dot product is equal to 0, but unlike 2 dimensions, we have another situation. There'll be skew if the lines are not parallel and do not intersect. Now, of course, that doesn't happen in 2 dimensions. In 2 dimensions, if they're not parallel, they have to intersect. But in 3 dimensions, they don't. We know parallel lines, they'll stay the same distance apart and never meet. Okay, that's fine. We have intersecting lines. They will cut each other. And of course, we have perpendicular ones that intersect at right angles. But now we have this type of situation. See, I've got these lines, they're on parallel planes, but the actual lines themselves are not parallel. Yet they don't meet because they're on parallel planes. So that's what we call skew lines. I want to show this, that this first line is skew to the other line. Well, the first thing I'm going to check, because this is the easiest thing to check, is are the direction vectors multiples of each other? Because if they are, then I know they're not skewed because they're going to be parallel. And in this case, looking at it, well, yeah, 1, 1, 0 could never be written as a multiple of 1, 4, 5. So no, We know they're not parallel. So the next thing we have to show then, if they're going to be skew, is that there's no point of intersection. Let's look at the components. 1 plus lambda is mu, 3 plus lambda is 4 mu, -1 equals 5 mu. I'll equate 1 and 3 and I get that mu is equal to -1/5. That means lambda is -6/5. Okay? If I equate 2 and 3, I end up with lambda being -19/5, which is not -6/5. So I've got different values, so they don't intersect. We know they don't intersect, we know they're not parallel, my lines are skewed. Last year's paper, they gave us this position vector and a vector equation of another line. B is on that line and it has position vector, well, Pi, Pj and 2pk. Show that the magnitude of AB squared is equal to this. Well, position vector of OA is 8, -6, 5. Of OB, it's PP, 2P. We don't know what P is. But if I was to find the magnitude squared, just square each of those components, P minus 8, P plus 6, 2P minus 5, and yeah, we get our quadratic. Hence, or otherwise, determine the shortest distance between the point and the line. Because have a look, it's a quadratic. If I want to minimise this quadratic, minus the discriminant on 4a, sub it in, 101. So therefore, the shortest distance is the square root of 101. So if you spot things like, hey, this is a quadratic function, they're asking me for a minimum or a maximum, I don't have to muck about. I can use my quadratic theory. That, oh, okay, I know the y value of the vertex is minus the discriminant on 4a. So 5f, playing with vector equation of line.